So hello everyone and welcome to Spectral Geometry in the Clouds. Today it is a pleasure to listen to Charlotte Dietze, who is going to talk to us about the Weyl formula and concentration of eigenfunctions for singular metrics. As usual, don't hesitate to ask questions even during the talk. My understanding is that you will be very welcome to do so at some point at least. If you have questions and you can't unmute yourself for some reason, you can share them in the chat and I will relay them to the speaker. So Charlotte, don't worry about it. Charlotte, the virtual floor is yours.
Good. Thank you very much, Laura, first for the invitation and giving me the opportunity to speak here. As Laura has mentioned, I'm really happy to take all sorts of questions. I think we have plenty of time, so feel free to just unmute yourself and ask. So what I'm going to talk about today are some Weyl asymptotics for Riemannian manifolds with a singular metric that is singular at the boundary. And this problem is motivated by some models for gas giant planets. And I will first explain a bit on the physical motivation and then come to the math. And the first part of my talk is joint work with Yves Colin de Verdièe, Maarten and Emmanuel Trélat, which is the part on the Weyl asymptotics and also on Weyl measures. And then there's a very last part on the speed of concentration of eigenfunctions, which is joint work with Larry Reed. I would first like to start with some physics motivation. And what we want to consider are big gas planets. So for instance, you could imagine Jupiter or Saturn, or also Uranus and Neptune, as over here. And one thing physicists would like to understand is what is going on in their interior. And to this end, like you cannot just directly observe it, like you cannot just slice the planet and have a look at what's happening in the interior. So one needs to measure things indirectly. And one thing among many other things they measure are data coming from the propagation of sound waves, so seismology on these planets. And this is what we are going to focus on in this talk today. So to understand the propagation of sound waves in the planet, and maybe using that, one could also try to understand a bit the properties of the planet and how these sound waves propagate inside the planet. And now you might ask, okay, but how do people even measure sound waves inside a gas planet, which is very far away? And there are many different ways of measurement, and I would just like to give you an idea of one of them, which I personally find the easiest to understand, and actually very surprising that it works, which is a ring seismology for Saturn. So if you imagine you have some sound wave propagating inside your planet, and if it's a non-radial sound wave, then what will happen is that this will change the gravitational field of your planet. So in particular, it will also have an influence on the small particles which are in the ring of Saturn, which will move a tiny bit as the wave propagates. And now if you think of some oscillation like some eigenmode of the planet, then you will see some small oscillation in these particles in the ring of the planet. And what physicists then do is they fly past the planet with a spacecraft and observe some star very far away through the ring of Saturn. And since these tiny particles move a bit, the intensity of light they measure when looking at the star through the ring will change and will oscillate a bit. And from this, they can deduce information on different eigenfrequencies. So it's not just some theoretical thing, but this can actually be measured. That's the good news. Now you might ask, well, what is special about gas planets? The one special thing which will also have, which is also reflected by our mathematical model, is that in gas planets, the speed of sound goes to 0 as you approach the boundary. And this is not true, for instance, for some rocky planets. So that's the main difference. And on the mathematical model, we will see this on the next slide, that this is reflected by a metric that is singular, a Riemannian metric that is singular, where the speed of sound goes to 0. So let me now go to the next slide, introducing the model. So I will work in general on X, which is an n+1 dimensional compact Riemannian manifold with boundary. But if you really just want to think of a planet, you can take X as being a ball, and then the boundary of the planet is just a sphere. but this is just an example. We work in the general setting. Another thing, well, if you look at X close to its boundary, then you can say it's diffeomorphic to an interval, which essentially across M, where M is something you can think of as your boundary manifold G. So you can think of M as the boundary of X. And this 0, 1 indicates some transverse coordinate U. So you pick some transverse coordinate U to the boundary, and you say that U is equal to 0 at the boundary, and then it grows as you go inside. Now I'm ready to tell you what kind of Riemannian metric I would like to look at. So I told you that the speed of sound in my gas planet will go to 0 at the boundary. And this means that I will consider a Riemannian metric G on my manifold that is singular at the boundary. And it is singular in a controlled manner. Namely, we consider Riemannian metrics G that are of the form 1 over U to the alpha, where U was this transverse coordinate, times G bar, where G bar is a nice, smooth, non-degenerate metric on the whole manifold. And smooth and nice and non-degenerate up until the boundary. So we have all the singularity in this 1 over U to the alpha. And alpha is a parameter that depends on the chemical decomposition of my gas planet. So what kind of gases there are. So it's mostly hydrogen and helium, but there are also some heavy metals, and they seem to indeed affect this alpha a lot, even if they're just small traces of them. And alpha will be somewhere between 0 and 2. Okay, so that's the kind of metric we want to look at. Now I would like to comment a bit on the cases where alpha is 0 and alpha is 2. So if alpha is 0, then we're just left with a nice, smooth, non-degenerate metric up until the boundary. And you can essentially think of this as the situation on rocky planets. So this is not the situation of the gas planet we want to look at. That's why we look at an alpha which is strictly positive. Then the other extreme is that alpha is equal to 2. And if you think of G bar, so say for instance, just being Euclidean metric, and you consider, say, just the upper half plane, and you take alpha equals 2, then you're left with nothing but the hyperbolic space, namely just the upper half plane model for hyperbolic space. So the alpha equals 2 would correspond to a hyperbolic geometry. And this is also not what we want to consider, because in the end, we will see on some later slides that if alpha is between 0 and 2, then we will have a discrete spectrum for our Laplace-Beltrami operator coming from the metric M, whereas if alpha is equal to 2, in the hyperbolic case, we do not have some discrete spectrum. So, and from physical observations, it seems like this alpha is always between 0 and 2, and strictly between the two. Okay, very good. So then now, on the next slide, I would like to present some changes of variables to get the metric in a nicer form. So first of all, one thing you can do, so the metric was G was nothing but 1 over U to the alpha G bar. And the first point I would like to make is that if you choose suitable coordinates, so if you choose the suitable coordinate U, which was this transverse coordinate, and the coordinate Y, which is on the boundary manifold M, if you choose them in a good way, then you can sort of diagonalize your metric G, and you can write it in, or you can call it a normal form. You can write it in the form 1 over U to the alpha, and then some du squared plus G0 of U, where the G0 of U, these are just a family of metrics. So if I fix a U, then the G0 of U is nothing but a nice Riemannian metric on the manifold, the boundary manifold M. And now, if I vary U, this gives me a whole family of these metrics, and they should be such that they vary continuously depending on U. Now, the next thing I would like to do is to do a change of variables. Namely, instead of looking at the coordinate U, I would like to get rid of the singularity here in front. And you can do this by defining X as essentially U to the power 1 minus alpha over 2, or more precisely given by this formula. And then you can write the metric G in a form which, at least for our proofs, looks a bit nicer, namely as dx squared plus x to the minus beta, and then a G1 of x, which is again some family of metrics on this boundary manifold M, depending on x. And now beta, now I've changed from alpha to beta, beta will be given by nothing but 2 alpha divided by 2 minus alpha. So if alpha is equal to 0, then beta is equal to 0, and if alpha converges to 2, then beta converges to infinity. So next, I would like to mention a few facts on this metric and together with the manifold X. And the first one, which is very different from the case of hyperbolic geometry, is that if you take any point in your manifold X and you ask yourself, what is the distance of this point to the boundary, then this is a finite number. Recall that in hyperbolic geometry, you would have an infinite number here. Another thing that is interesting is about the Hausdorff dimension of the manifold X, including its boundary with respect to, well, with G. This is not, so the topological dimension of X was n plus 1. So we said we have an n plus 1 dimension manifold. But since we have a singularity of the metric, if we compute near the boundary, if we compute the Hausdorff dimension, we find that it's n plus 1, or it's n times 1 plus beta over 2, if that value is larger. And you can see that if you take beta very large, then this Hausdorff dimension will diverge. And there's a critical value for beta where things change, which is exactly at 2 over n. Another thing, this critical value is not only interesting for the Hausdorff dimension, where the Hausdorff dimension changes, but also it's interesting for the corresponding Riemannian volume measure. Namely, when beta is smaller than this critical value, we have a finite Riemannian volume measure, whereas for beta equal or larger than this number, it's infinite. Next, I told you that it's all going to be about the Laplace-Beltrami operator. Now, after doing a few steps, namely, we do some change of function as well, which I might explain in more detail afterwards. You can write the Laplace-Beltrami operator in the following form, namely, it's near the boundary. This is near the boundary, but inside the manifold, everything is nice and smooth. So we only need to, the part where we really need to do something new is at the boundary. And near the boundary, you can write it as minus dx squared plus a constant divided by x squared plus x to the beta times the Laplace-Beltrami operator on the boundary manifold M with respect to the corresponding G1 of x equals 0. So there are a few steps I've hidden here. I used some quasi-isometry and some change of functions, but I will come to these points later in the proof. So let's just accept this formula for now. And this constant C beta has some explicit value you can see over here. This operator, well, this is the operator which we need to understand better if we want to understand something about the spectrum. But also at this point, it's maybe interesting to note that if you take the first term and the third term, then together this gives us some Gaussian type operator. So for instance, for beta equals 2, it's the usual Gaussian operator. And then we have some singular potential like 1 over x squared. So this also gives some link to sub-Riemannian geometry. Now, one fact, which I've already alluded to previously, is that since our alpha was between 0 and 2, one can show that the Laplace-Beltrami operator has discrete spectrum. In fact, we take the Laplace-Beltrami operator with Dirichlet boundary conditions, so the corresponding Friedrich extension. And morally speaking, I would say that it's not a proof, but I would say morally speaking, this should be linked to the fact that every point has a finite distance to the boundary. So it's not so much about volume being finite or infinite, because we have both cases here. Okay, so now that we know that we have discrete spectrum, a natural question is, well, what about the asymptotics of the eigenvalues, lambda j? And to this end, I define n of lambda, which does nothing but it counts how many eigenvalues there of the Laplace-Beltrami operator there are, which are below lambda. So for instance, in this picture here, I fix a certain lambda, and then there are 3 eigenvalues below. So this n of lambda for this picture is 3. And then what I would like to do next is to understand how n of lambda behaves for lambda very large, to get some asymptotics. And this is the result which we have proved, which is giving some Weyl asymptotics for this n of lambda in 3 different cases. So we, as we've already seen, there was something special happening as this critical value for beta, which was 2 over n, where somehow the Hausdorff dimension changed from being n+1 to being larger than that. And so the theorem has, well, these 3 cases, beta being smaller, equal, and larger. And if beta is smaller, then what we can show is that the n of lambda behaves like the classical constant in the Weyl law times the Riemannian volume of X with respect to G times lambda to the power n+1 plus lower order terms. So if you think of a nice, smooth, non-degenerate Riemannian manifold, possibly with a boundary, that's what you would expect for the Weyl asymptotics. So far there's nothing too special. Now, if beta is equal to the critical parameter, then I've already mentioned that this volume term here will be infinite. So, well, we cannot expect the first line for asymptotics to be true. And indeed, what happens is that instead of having some behavior like lambda to the power n+1 over 2, we get an additional logarithmic factor over here. So it behaves like lambda to the power n+1 over 2 times the logarithm. The other thing that is interesting is that we have a volume term of m computed with respect to the Riemannian metric G1 at x equals 0. So this term is something that only cares about what happens at the boundary. And I will comment on this later, what this tells us. Now you could go even further, and namely you can take beta larger than the critical value. And for this one, we could show that, again, we have some constant that depends on n and beta. We again have some volume term that sees essentially what happens at the boundary. And then we have a power lambda to the Hausdorff dimension over 2 plus lower order terms as lambda goes to infinity. So in all of, at least in the first and the third case, we have some behavior like lambda to the Hausdorff dimension over 2. So in the first case, the Hausdorff dimension was also n+1. And in the critical case, we have this additional logarithmic factor. And the other thing to keep in mind is that while in the first case, in the subcritical case, we have a volume term, in the critical and supercritical case, we only seem to care for the leading order asymptotics for what happens at the boundary. Now, we are not the first ones to prove some results in this direction. And in fact, Bosquin and collaborators, they have proved these asymptotics for the second case, for the critical one, for the hemisphere with an explicit metric. So they considered beta equals 2 over n and n equals 1 with an explicit metric, and they got the same kind of formula. Also, very recently, there has been a paper by Chitur, Prandi, and Rizzi, and they had different assumptions, but what they proved was essentially the first and the second case, similar to what we have done. But then in the supercritical case, which is the most challenging one, they could not get the precise asymptotics, but they could get some bounds. So they could find some constant which was not optimal, and saying n of lambda is less than or equal to that constant times lambda to the Hausdorff dimension over 2, and larger than or equal to another constant times this factor. Okay, and so the main difficulty for us was also actually to get the supercritical case here. Good. Now it's time for some pictures. This, as far as I have understood, these are simulations for different eigenvalues for a planet, in the case where beta is larger than the critical parameter. And so on the top, you can see the different eigenfrequencies, and from the lambda j, they will correspond to a constant times the frequency squared. So from these, essentially, you could compute the lambda j. And here, well, the colors you can see, they tell us something about the functions, namely when it's blue or when it's red, the absolute value is very high, and when it's green, it's more or less close to 0. And one thing that is interesting, which can already be seen in this picture, is that somehow, at least for most of them, we seem to have some sort of things seem to happen at the boundary. Like there are many things more or less localized at the boundary. And this seems somewhat reasonable given that in the first leading order term we have seen that the only thing that really seems to matter is what the metric does at the boundary. So if you change the metric in the interior for the leading order asymptotics, that would not matter. Okay. But well, these are just some simulations. So next you could ask, well, what about, can you actually prove something about where these eigenfunctions are? So here in this picture, it seems like they will be localized near the boundary, but is that really true in general? And for this, we have the following result, which is on Weyl measures. So it's again asking where are the eigenfunctions localized? And whereas in the picture on the last slide, I had some planet which was more like an ellipsoid, so it was not exactly round. Here we have some other pictures from a simulation where the planet is just a full round planet. And it's again for some value where beta is larger than the critical parameter. And again, you can see that the eigenfunctions essentially concentrate near the boundary. Now, from a mathematical point of view, we would like the next theorem is on Weyl measures, which gives us, in some weak sense, tells us where most of the eigenfunctions will be localized. Namely, our theorem says the following. So we can find some probability measure, WG, and the probability measure will depend on beta, on a manifold, and so on. So that no matter which test function f I pick, and test f will be a continuous function on x, if I take lambda very large of the expression we have here, then it will converge to the integral of f computed with respect to that probability measure. So what do we have on the left-hand side? First, let's pick f equals 1. So the phi j are nothing but normalized eigenfunctions, so they're normalized in the L2 sense. So if I pick f equals 0, then for each of these phi j, this integral will give me 1. Now I sum over all the lambda j, so all the eigenvalues lambda j, which are less than lambda. So this gives me, if I take f equals 1, this gives me the total number of eigenvalues less than lambda. And then I divide by this n of lambda. And now if I take lambda, well, this, if I just take f equals 1, gives me 1, which, well, agrees with what I have on the right-hand side. And now if I take another test function f here, this will tell me in a weak sense where these eigenfunctions phi j squared are localized in the limit as lambda is very large. And what we proved is the following. So first, in the case where beta is smaller than the critical value, this probability measure WG, which you have here, will be the uniform measure on the manifold X computed with respect to the corresponding Riemannian volume measure. So you take essentially that measure, but then you need to normalize. So it's a probability measure. If beta is larger or equal to the critical parameter, then we see a picture similar to the one on the previous slide and also the one we have here. Namely, the WG will then be essentially a delta distribution on the boundary, or more precisely, it will be the uniform measure on the boundary with respect to the Riemannian volume measure coming from G1 evaluated at x equals 0. So this somewhat makes it rigorous to say that most of the eigenfunctions are concentrating near the boundary as my lambda gets very large. So on the next slide, I would like to go a bit more into detail, and in particular, I would like to focus on the second point over here. So we've seen that we have some sort of concentration near the boundary, but one question you could ask is, can we understand the rate of concentration near the boundary? How fast eigenfunctions accumulate at the boundary? And this is the last theorem, namely, and we could only do this for the case where beta is larger than the critical value. So as an open question, one still needs to understand what happens at the critical value. And essentially, let's maybe go back to the explanation at the bottom of the page first. Essentially, what we could prove is that these eigenfunctions, if you think in the x coordinate, which we had introduced, which was some power of u, then these eigenfunctions concentrate at a rate 1 over square root lambda at the boundary. And in the corresponding u coordinate, one can then do a change of variables and see that as lambda to the minus 1 over 2 minus alpha. So we get a rate of convergence, how fast the eigenfunctions accumulate at the boundary. And what we will also have is we will get some profile on how they accumulate. But let's now have a look at the theorem more precisely. Depending on my beta and my metric and so on, my claim is that I can find a b, which is a positive function, which is an L1 with L1 norm equal to 1, so that no matter which bounded and continuous test function v I plug in, so v is essentially a version of the f from the previous slide. If I look on 0 infinity cross m, so I'm somehow looking only at what happens near the boundary, because we know already that most of the eigenfunctions concentrate near the boundary, I have the following. So the expression I have here looks almost the same as what we had on the previous slide. The only difference is that instead of taking f or f of x, y, we now rescale our test function v in x. Namely, we take v of square root lambda x, y. So this means nothing that we zoom in at a scale 1 over square root lambda. And then again, after zooming in, we multiply by the normalized eigenfunction squared. We sum over all the eigenvalues which are less than lambda, and then we divide by n of lambda. So again, this v gives me a zoomed in version of the f. And now if I take the limit lambda going to infinity, what we can show is that you get the test function v of x, y back, and multiplied by some b of x, which gives us the rescaled profile of the eigenfunction squared, where we rescale at a scale of 1 over square root lambda, and then we integrate with respect to the corresponding measures. And so in short, what it tells me is the fact that I have here the square root lambda tells me I concentrate at a rate, or my eigenfunctions accumulate at a rate 1 over square root lambda near the boundary. And the b gives me the rescaled version of the profile. So if I zoom in at that scale, what is the profile that emerges in a weak convergence sense? Now next I have some short summary. So to see what we have done so far. Namely, what we've seen, what I told you about at the very beginning, is that the speed of sound in gas planets goes to 0 near the boundary, and that we would like to model this using a Riemannian metric that is singular at the boundary. And the kind of metrics we are considering is something like 1 over u to the alpha times some nice metric which is non-degenerate up until the boundary. So we have a singularity of a very predefined type. And in order to understand the eigenmodes of the planet, we can study the corresponding eigenvalues of the Laplace-Beltrami operator. And we've seen that the asymptotics of these eigenvalues, so this was the theorem on the Weyl theorem, this heavily depended on the material-dependent parameter alpha, which was then expressed in terms of the beta. And we've also seen that for certain regimes of alpha, the eigenfunctions localize near the boundary, whereas for others, they more or less stay well inside the domain. And then the very last result which we've had was that in the supercritical regime, a rate of convergence of how fast these eigenfunctions concentrate at the boundary, which was in the u coordinate at a scale lambda to the power minus 1 over 2 minus alpha. Okay, so I have some details on the proof prepared, but I think it's a good time maybe if some of you have some questions to ask them now so people don't get too lost. So if you have some questions, feel free to ask.
Yes, Charlotte, I do have a question.
Yes.
It's about, do you know what is the decay of your function B, the big B?
No, we didn't compute
No,
it.
but the B is explicit, but what is the decay? It is fast decay at x going to infinity, or?
I think it should be, so I would have to check. We have an explicit formula, but it's explicit in terms of some, like it's an averaged version of eigenfunctions of a corresponding one-dimensional operator that will later appear in the proof. And so one would have to do is to analyze how fast these eigenfunctions decay. So I guess one could probably use some Agmon type estimates to get some exponential decay. And then since it's an averaged version of those, one has to check that you would still get it, but I would personally guess it's some exponential decay.
Because then it gives a precise localization at some distance.
Yes.
And after it's very small.
Yeah.
Okay, thank you.
So I mean, I would have to check, but if you ask me to guess, I would say it's some sort of exponential.
I'm not sure. I've seen your formula, of course, but I don't remember it. Okay, thank you.
Yes, Charlotte, I wanted to ask, does that mean that you could understand the value of alpha based on some numerical data on your plan?
Yes, so in principle that should be possible, and to get the value of alpha in terms of the data. So if you have numerical data, of course, but also if you have observations, you should be able to deduce the value of alpha. And one of my collaborators has some contacts to experimentalists who are actually measuring. And as far as I've understood, at least it seems that the model they are currently using, or they're currently considering to be the best, has some, for Saturn, for instance, has some slightly supercritical value for the alpha. So but that's the latest information I have, and we will probably have to look into more details. Yeah. But this is actually one of the things I'm curious about, to really get these values for different planets.
To be honest, I think my next question is, can I know more about the proof?
Okay, then maybe I just continue with the proof. So I've done some sort of summary slide, so we know what we are going to prove, and then I will tell you a bit about the proof details. So what we've seen, we had our n+1 dimensional compact Riemannian manifold with boundary, which I called big X. Initially, we had written everything in terms of a transpose coordinate u, but then I had told you that we can do a change of variables and have some coordinate x. And using the coordinate x, my Riemannian metric near the boundary reads like dx squared plus x to the minus beta times g1 of x, where these g1 were nice, smooth, or nice non-degenerate metrics on my boundary manifold M. So near the boundary, I said this is written a bit in a bad way. So the Riemannian metric near the boundary is this, and then x near the boundary should, so forget about this, x near the boundary should be written in this form. So it should be like have some interval in x, and then cross the boundary manifold. And I will call the coordinate on the boundary manifold, I will call that y, as we did also in the theorems for the concentration. Then we've seen that we had this critical value of beta, which was 2/n, and that was the point where the Hausdorff dimension changed, namely from being the topological dimension n+1 to a larger value. And the proof I would like to explain is on the first theorem I've mentioned, which were the Weyl asymptotics. So we had some asymptotics for counting the numbers of eigenvalues for the Laplace-Beltrami operator coming from the metric G. And we had different cases depending on whether this beta was subcritical, critical, or supercritical. Okay. And in the paper with Yves Colin de Verdièe, Maarten and Emmanuel Trélat, we use heat kernel methods in order to prove this theorem. But we also have a remark telling that you can also prove the theorem alternatively using Dirichlet-Neumann bracketing. And in the following, I would like to explain you some of the main steps on how the proof can be done using Dirichlet-Neumann bracketing. Good. So it's just a rough strategy, so please feel free to ask if you want to have some more details. It's really just to give you an idea of the main steps. So the first step is to split my big manifold, X, into the region very close to the boundary and everything else. And the region very close to the boundary at a scale epsilon, I will call this X epsilon, and then we have the rest. So X epsilon is the blue part in my picture. And it corresponds to, in these local coordinates, it corresponds to 0 epsilon cross m. And epsilon in the end will be chosen sufficiently small. then what we can do is, well, using Dirichlet-Neumann bracketing, we can say, well, what we're interested in is counting the numbers of eigenvalues which are less than lambda of the Laplace-Beltrami operator. So this is the object in the middle. And from Dirichlet-Neumann bracketing, what we know is that it's larger than if you take the numbers of eigenvalues less than lambda just on x epsilon, so just on the blue part, where I put Dirichlet boundary conditions on the red part. So this just corresponds to x equals epsilon, plus the numbers of eigenvalues again with Dirichlet boundary conditions at x equals epsilon for the part inside. So the total numbers of eigenvalues is larger than this with Dirichlet boundary conditions, and it's smaller than the corresponding thing with Neumann boundary conditions at the red circle. Okay. So if we can get some good if we can prove the asymptotics for what is on the right-hand side and what is on the left-hand side, and if these agree, then we are done with proving the asymptotics for n of lambda. So the strategy is to get good enough asymptotics so that the asymptotics of the right-hand side and the left-hand side agree. What we do know relatively well is the asymptotics for the numbers of eigenvalues in the interior part. So on x without x epsilon, so this is the white part you can see here. The reason is that in this part, our metric G is non-singular. So we can use standard theorems from Riemannian geometry. And essentially we get the usual classical Weyl constant. We get a volume term of the corresponding part and a lambda to the power n plus 1 over 2 plus lower order terms. Now, in order to prove the asymptotics, well, we can distinguish two different cases, namely if beta is smaller than the critical value, then the result we would like to prove was nothing but this formula up here, just with an x. So there the idea is to show that the other terms, namely the terms coming from the blue region, they will be of subleading order. Or more precisely, we can show that they're less than or equal to a constant, which will go to 0 as epsilon goes to 0, times lambda to the power n plus 1 over 2. In the critical and supercritical case, the asymptotics we wanted to show is different. And in fact, there will be more eigenvalues than we have here, like more than lambda to the power n plus 1 over 2. So the idea is to say, well, we want to show the corresponding asymptotics for these parts, for the parts on x epsilon. And then the parts from the interior will be of subleading order. Good. Now, the next step is that for our metric, we had initially a metric. I call it now G old, because I will soon replace it by a new one, which is of this form. So we have a dx squared plus x to the minus beta, and then G1 of x, where these G1 were a family, depending on x, of Riemannian metrics on n. What we want for later purposes, it will be useful to replace this metric by a new metric, which I call G new, and then later I will just call it G, which is the same one, but I only take G1 at x equals 0. And since I said that these metrics G1 of x, they will vary continuously depending on x, if I only look at the interval 0 epsilon cross m, then it's indeed not, this G new is not too far from the old one. And in fact, you can show that they are quasi-isometric with some delta that depends on epsilon and goes to 0 as epsilon goes to 0. And thus what one obtains is that also we get some bounds on the corresponding counting functions, the n of lambda, which are almost the same up to some small constant if I take the G old or the G new on this thing. So this tells me instead of working with the old one, which has a bit of more complicated structure, I can also work with the new G, which looks simpler. The next step, which I have, so far we've split our domain into two parts, the boundary region and whatever is inside. And for the boundary region, we have said that we want to replace our metric by a new metric, which looks nicer. Next, also for the boundary region, I would like to explain you the change of function and measure, which I have briefly alluded to in the beginning. Namely, if you well, if you consider it for the new metric we have here, then the corresponding Riemannian measure will be of the form x to the minus beta n over 2 times dx dv1 of x, where this dv1 comes from the metric dv1 of y, where this comes from the metric g1 at x equals 0. And we consider functions f, well, we will consider functions in the corresponding L2 space on this space with the corresponding volume. Now, the change of functions is that instead of considering some function f tilde, I would like to consider the corresponding function f, where f of xy is x to the minus beta n over 4 times f tilde. And then if I define a new measure dv of xy as just dx dv1 of y, so this is a much simpler form, so this will be much more convenient to work with, then one can check that we have an L2 isometry, namely if I consider f tilde multiplied with some other function h tilde, or you can just think of f2 tilde if you want, with this measure dvg, then the integral will be the same as if I take f times h with the new measure integrated over the domain. So using this, what I've gained is that I have some nice measure here which doesn't have any weight, and this will make our analysis much simpler. Okay, and now if you sit down and do the computation, what you can find is that after doing this change of function, the Laplace-Beltrami operator now has the form which we have already seen at the beginning of the talk. Namely, you have the minus dx squared plus the singular term c beta divided by x squared plus some x to beta times the Laplace-Beltrami operator on m. And again, the c beta was some explicitly given constant. Now, the reason why this is very good for us, and this is, I think, also one of the main reasons why this change of the Riemannian metric to the new one is really helpful, is that now we have an orthonormal basis of eigenfunctions of our Laplace-Beltrami operator that are in a product form. So they are some function depending on x times some function depending on y. So more precisely, we have to consider two cases because we said we do Dirichlet-Neumann bracketing. So either in the red region, we have Dirichlet or Neumann boundary conditions. And since I, in the very beginning, mentioned that we are considering the corresponding operator, Laplace-Beltrami operator with Dirichlet boundary conditions on x, we always have Dirichlet boundary conditions at x equals 0. And well, okay, so what we can show is that we can find an orthonormal basis of eigenfunctions. I will call them phi of alpha mu, depending on x and y. Alpha and mu are some parameters. And they will be of the form some function, depending both on alpha and mu of x, times another function, depending only on mu on y. Now this psi mu of y, so the idea is, I first take a psi mu of y, which is an eigenfunction of the Laplace-Beltrami operator on M with eigenvalue mu. I multiply it with some function here. So if I look at the corresponding on the level of the Laplace-Beltrami operator, this is good because it this part from the psi mu will just tell me that essentially I can replace the Laplace-Beltrami operator by mu. And now I get an equation just for the x variable. So this is how I get the separation of variables. And the equation for the x variable is, well, this phi alpha mu. If the big phi is an eigenfunction of the Laplace-Beltrami operator with eigenvalue alpha, then this little phi alpha mu is an eigenfunction of this operator p mu, which is the Laplace-Beltrami operator I've written here, but instead of the Laplace-Beltrami operator on M, I just write mu. And this phi will be an eigenfunction of this operator p mu with eigenvalue alpha. Okay, so now we're in a good shape. We have written an orthonormal basis of eigenfunctions in a product form. So now if I want to count the total number of eigenvalues, that's what we're after, then I can do this depending on understanding the numbers of eigenvalues of p mu, and also understanding the corresponding eigenvalues of the Laplace-Beltrami operator on M. But that one is less of an issue. So what we can show then very directly is that if I want to compute the numbers of eigenvalues on this boundary manifold X epsilon that are less than lambda, this is nothing but taking the sum over all the mu j, where the mu j are the jth eigenvalue of the Laplace-Beltrami operator on M. And now I take eigenvalues of p mu j, which are less than lambda. And I just sum up over all the different values of mu j I can have. And this gives me the expression on the left-hand side. So now I've replaced the total number of eigenvalues by a sum, but now I only need to understand asymptotics for eigenvalues of p mu for different values of mu. Again, these mu j are not very dangerous because the G1 is a nice Riemannian metric on M. So we have the usual Weyl law on M, and we can show that the mu j are some constant that depends on the volume of M and the dimension n times j to the power 2 over n plus lower order terms. So we can, and essentially, well, one has to justify this, but essentially, morally speaking, you can replace these mu j by this constant times j to the power 2 over n up there. Another really important thing we use, and this is really the main thing which makes our proof work in the case, in the supercritical case, is that we have some isometry, namely the operator p mu is isometric to mu to the power 2 over 2 plus beta times p1. So this means if I want to understand the spectrum of p mu, alternatively, if I compute the powers correctly, it suffices for me to just understand the spectrum of p1. So then, doing a few intermediate steps, which I'm now skipping, what one can do is if you, for instance, multiply by lambda to the power minus d over 2, and you take this object you have over here, then you can show it's, lambda to the power minus d over 2 times the sum, and now you have the eigenvalues of the operator. So here I wrote the mu j to indicate that I'm looking at p mu j. Now I'm looking at p1, but on a larger interval. So this epsilon times mu j to this power will become a larger and larger interval. So essentially, you will be able to replace this by just a half line 0 infinity. And we need to consider now eigenvalues that are less than lambda times mu j to the power minus 2 over 2 plus beta. And now, which I will not explain in detail, what you can do is if you replace this mu j by this expression over here, so essentially by j to some power, then one can check that this over here is nothing but a Riemann sum, which in the case beta larger than this critical value converges to a Riemann integral. And this will give us the constant in the Weyl law. And this is in the supercritical case. In the critical case, you can actually see that these ones will be essentially like a 1 over j, and they will give us the logarithm, which we could see in the Weyl asymptotics. So what was important here are, and then the only thing one needs to understand, so one remains with some object that depends on the P1, but for the P1, again, it's not too difficult to understand the Weyl asymptotics. So the main idea here, which made the proof work, and this was crucial, was to first use scaling. So first we use this scaling to get from P mu to P1, and then afterwards to use the Weyl asymptotics for P1. If you try to do the other way around, which we initially did, then you get some error terms which are too large. So everything works due to scaling and then using the Weyl asymptotics for the simple one-dimensional operator P1. Okay. And with this, I think I'm done with explaining the proof strategy. So you can, I just put again the summary slide from before.
Thanks a lot, for this talk. We have time for some questions now. So if you have some questions, please unmute yourself and ask them or write them down in the chat.
Do you think there's any way of improving the remainder in the Weyl law? Like gaining an exponent or something like that, or log?
So, okay, let me go back to the theorem. So, I would believe that for the subcritical case, so the first one we have over here, this should be possible, or could very well be possible. Essentially, what one would have to do, or where would you have to improve the proof we currently have? Currently, we said I use this quasi-isometry. So in a small boundary neighborhood, I just replace my metric by the one where instead of g1 of x, I just take g1 of x equals 0. And if I want to improve on, if I want to get, say, a second order term, what I would have to do is I need to do a more precise approximation here. So for instance, I could imagine taking some sort of Taylor expansion for the G1, and then I would be at least hopeful that you could get some second order term here. However, well, this is for the subcritical case. In the critical and supercritical case, I'm not so optimistic, to be honest, because it was, to me at least, it was almost like a miracle that we could get actually one constant here and not some bounds as in previous papers, because it was really a fine thing of first using scaling and then using the Weyl asymptotics and not getting too large error terms. And we heavily relied on this fact that you have separation of variables. So I believe that this would be a big issue if you try to linearize. It might still be possible, but I would first try for the first one. And I would believe that you can, in the first one, so one thing that is interesting in the first one, so one thing you could ask is, as an inverse problem, you could ask, suppose I know the spectrum, can I tell you which value beta has? And if beta is critical or supercritical, we can see that even from the leading order asymptotics, we get the value of beta. Namely, here it's contained in the Hausdorff dimension, and here we see it because we get a logarithm. But in the subcritical case, we don't see the value of beta immediately, and I would believe that this will pop up in the second order term, similar to a usual Weyl asymptotics, which gets some boundary term in the second order term.
Thank you, Laura, for the question. And
just a complement to the answers. In the critical case, as far as I remember in the paper by Boscain, the next term is the same but without the log. So it's just the power lambda, log lambda, plus another term which is lambda. And another observation is, I guess, if beta is close to the critical value, I don't hope to have a better term than O of the topological dimension divided by 2, because you have to include what happens in the interior of the domain.
Yes.
So I guess at least you have to have lambda to the topological dimension.
You mean like for the supercritical case, right?
Even the critical case.
Yeah.
I agree that in the subcritical case, you can maybe get a better reminder, but I'm not sure how to do it.
thanks, Yves, for the clarification. Do we have other questions for Charlotte?
That I have a remark about some things we are trying to do with Charlotte, Emmanuel, and Maarten. One thing we try to do in the supercritical case is to get some kind of quantum ergodicity if the geodesic flow on the boundary is ergodic. Because we expect because we know that the eigenfunctions, they do concentrate on the boundary, and the dynamics should be the geodesic dynamics, because it is the case in the separable case, namely if G1 is independent of X. Then you have really eigenfunction of the boundary times function on X. And another much more difficult question, I guess, is the case where alpha is not a constant. Then we expect some behavior which is close to what happens for alpha is a maximum. The most singular, there are some points at the boundary which are more singular than others, and we expect of concentration near those guys. Okay.
Correct.
So maybe I can comment a bit on the last point Yves mentioned. So
Yeah.
Go
on. Is that you would expect concentration near the point where the alpha is the largest. And the way you can see that, at least intuitively speaking, is, say, suppose you have alpha, which is, say, piecewise constant, and you want to compute the corresponding Weyl asymptotics. Then you would expect to get essentially a similar formula, but now let's suppose I have my domain M, like the boundary manifold, and I just decompose it into two parts, and one is like value alpha 1 or beta 1, and on the other one the value beta 2, and say beta 2 is larger than beta 1. Then what you would get is you would get one term where you have the M1, and then you have the lambda with the corresponding Hausdorff dimension for beta 1, and then you have another term with the M2 and the lambda with the Hausdorff dimension for beta 2, plus lower order terms. But the term with lambda to the Hausdorff dimension of beta 2 is much larger than the one for beta 1, because this dh will just be larger. So essentially you will not see the first term. So this tells you really that the only thing that matters in the leading order asymptotics will be a volume term of the M2. And there you can already guess that things should happen near M2. And we have some very, very first results in this direction, but far from what we would like to get.
So isn't it the case, speaking of some sort of quantum ergodicity result, that in the Chitour, Pranzi, and Rizzi paper, there is in there some sort of notion of quantum ergodicity at the critical exponent?
I don't think so. It's a completely different method, and I don't think so. I never discussed that with Luca, but I guess no. It's completely different.
Yeah. Okay. Well, I mean, I may misremember from when I read the paper some time ago, but that's
Okay.
all right. Do we have other questions for Charlotte? All right.
Yeah, I have another question, but we were already discussing. If you look at you could look at the Neumann boundary conditions, or in sense of quadratic form.
Yes.
By taking at the domain smooth function up to the boundary, okay? Then I guess that lambda 1 is 0 in the subcritical case, but it's strictly positive in the other cases.
Yeah.
Because the constant functions are no more in the domain.
Not in L2. Yes.
And we started discussing, but with no result, about to get some lower bound or some bounds for lambda 1 in the supercritical case, and for Neumann. Because otherwise, I guess all the estimates Weyl asymptotics are the same. I'm not sure, but I guess they are the same.
Yeah. However,
I don't remember, because I don't remember. It is essentially self-adjoint in the supercritical case, no?
Yes. Yes.
Okay.
Yes.
So in the supercritical case, it's not important to look at boundary conditions. Otherwise, you have to look at boundary conditions.
Right. I think unless we have other questions, in this case, I think we can thank Charlotte again for this talk, and we will reconvene next week with a talk by Jeff Galkowski, who will tell us about the Steklov problem for piecewise smooth boundary. So thanks again, Charlotte, and see you next week, everybody.
Okay.